We're going to finish up our Unit 8 notes today with Example 5. A roll of toilet paper is held by the first piece and allowed to unfurl as shown in the diagram to the right. The roll has an outer radius of 6 centimeters, an inner radius of 1.8 centimeters, a mass of 200 grams, and it falls a distance of 3 meters. Assuming the outer diameter of the roll does not change significantly during the fall. Okay, so let's take a look at what we've got here. S, the distance that it falls, is 3 meters. Then we've got the inner and outer radii. The outer radius is 0.06 meters, that's 6 centimeters. The inner radius is 0.018 meters, that's 1.8 centimeters. And, we had the mass. The mass of the toilet paper roll is 200 grams, which is 0.2 kilograms. Okay, now this is a situation where we're going to have to incorporate two different sets of concepts that we've learned. We're going to have to think about the linear motion of the toilet paper roll, and we're also going to have to think about the angular motion of the toilet paper roll. We're actually going to have to think about both of them. So let's start with what we learned first, which is net force. So when we learned about net force, we learned that we should draw a force diagram. So down here, I'll draw a force diagram for the toilet paper roll. So at the center of gravity of the toilet paper roll, I will draw FG. And then it also has something pulling up on it, and that is a tension force, which in this problem they have labeled as just a capital T. Sometimes we write FT, but since they've labeled it as capital T, I'm going to keep it that way. Now, if you look at this as just a linear thing, we could think about taking this T, this tension force, and moving it over and drawing it from the center of gravity. I don't know if that's entirely accurate, but if you think about this in the linear sense, we have one downward force and one upward force, and we can write the formula for net force. So the formula for the net force is going to be the larger force minus the smaller force. The larger force is Fg, and the smaller force is T. So I'm just going to leave that there as my linear information for a moment. Then what I'm going to do is I'm going to think about angular motion. And much like the ruler example, which if you have not watched, you should go back and watch, we are going to use two different definitions of torque. We know that torque is equal to force times lever arm times the sine of theta. By the way, in this example, theta is 90 degrees. If this is the lever arm here, do that again. If we're thinking about this torque, or this T as a force, then this distance is our lever arm, and they are at right angles to each other. And the sine of 90 is 1, so I don't have to worry about that too much. So I can just basically say that torque equals Fr in this case. Another formula for torque that I can use is I, that's moment of inertia, times alpha. Okay, so what I'm going to do is I'm going to set those two formulas equal to each other. And if I say one formula for torque, F times R, equals the other formula for torque, that's I times alpha, let's see what I can figure out here. The F, the force that causes the rotation, is the tension force. The center of gravity is actually or the gravitational force is actually happening at the center of gravity. This is my pivot. That's kind of hard to see. So there's no torque being created by the gravitational force. So back up to the top here. So this F, this force causing rotation, is the tension. And this R is the, capital R is the outer radius of 6 centimeters. The moment of inertia of this hollow cylinder is 1/2 m outer radius squared plus inner radius squared. And then the thing I'm looking for is alpha, or another thing I don't know is alpha. So now let's just take a moment and look at what we're trying to do here. We're trying to find, in this question, we're trying to find the tension in the sheets. We're trying to find T. We have R, we have mass, we have R again, and we have inner diameter. We do not have alpha. The other thing that I'll notice is I have two equations, and if I can make two equations with the same two unknowns, in other words, if I can find a way to link this linear equation to alpha, then I can figure this out. So I'm going to have to make some more substitutions. I know that net force is equal to mass times acceleration, so I can make that substitution. And I also know that linear acceleration equals angular acceleration times radius. And that's what I'm going to have to use to find alpha, so I can have two equations and two unknowns. Before I get that far, though, I'm going to finish this out. Fg is equal to the mass of the toilet paper roll times g, and then T is unknown. And then I am going to make a substitution for acceleration. And I'm going to solve for, again, the thing I'm looking for here is alpha. I'm going to solve for alpha, so I'm going to divide both sides by mr. Okay, so now that I have that, I can take this and I can use it in my angular equation. So now I'm going to rewrite my angular equation. Okay, now normally I would solve this for T. This is kind of a algebraic disaster, so I'm going to go ahead and start plugging in values that I do know. I know the outer radius is 6 centimeters. I knew that inner radius is 1.8. I know mass is 200 grams. So I think I would be better off plugging in those numbers as I proceed. So the tension is unknown. This is outer radius is 6 centimeters or 0.06 meters. The mass is 0.2 kilograms. And then again, we've got 0.06 squared, 0.018 squared. By the way, this chunk right here, that is our moment of inertia. And when you calculate that out, it's 0.000392. That comes in handy again later. And then, let's see, now I'm going to do this last bit. 0.2 times 9.81 minus t over 0.2 times 0.06. All right, I'm going to bravely move forward here. So I'll have t times 0.06 equals 0.000392, and then times 1.962 minus t over 0.012. And then my next step, you can proceed obviously a lot of different ways from here, but my next step was to divide both sides by 0.06. And when I did that, I got that t equals 0.00653, and then times 0.1962 minus t over 0.012. Okay, we're getting there. And then I multiplied both sides by 0.012 and distributed the 0.00653. And when I did that, I got t equals 1.0682 minus 0.544t. Then I added the 0.544t to both sides, and I got 1.544t equals 1.0682. And then I divided both sides by 1.544, and I got that the tension in the roll was 0.692 newtons. Oh my goodness. Okay, so that was tedious, but not hopefully super difficult. It wasn't logarithms or anything. It was just kind of an algebraic adventure. Okay, so now we have that tension. So next I want to think about how I can use that to figure out my accelerations. It's actually easier to do the angular acceleration before the translational acceleration. So I'm going to do C next. And I could just use this formula right here, alpha equals mg minus t over mr. So that would be 0.2 times 9.81. And the outer radius was 0.06. And when I solve that, I get 105.9 radians per second squared. Once I have that, it's easier to go back to, so I'll just put a little 2 here to remind myself I did that first. Or I did that second. I did this first. Oops. Okay, now I'm coming to the translational acceleration of the roll. So I know that the translation or linear acceleration is equal to the angular acceleration times r. So that's 105.9 times the outer radius, which is 0.06. Remember that a radius is the meters per radian. And when I multiply that out, I get 6.35 meters per second squared. So this toilet paper roll, as it unfurls, it's falling and accelerating, but it's accelerating more slowly than the acceleration of gravity. Okay, the rest of this then is just kinematics. We're supposed to find the final translational speed of the roll. We know that the initial speed is 0. We know that the acceleration is 6.35. We know that the roll is falling 3 meters. And we want the final speed. So we can use kinematics. do that, we get that the final speed of the roll is 6.175 meters per second. And then again, to convert that to an angular speed is pretty straightforward, because angular speed is linear speed divided by the radius. So I would take 6.175 and divide by that outer radius, and I get 103 radians per second. All right, there you have it. Everything you wanted to know and more about unfurling a roll of toilet paper.